Hey there, young scientists. Imagine you're standing at the top of a hill, holding a rock in your hand. What happens if you let go? The rock falls, right? Well, before it falls, that rock has potential energy. It's like energy on pause, waiting to do something when it's given the chance. Potential energy is energy that's stored because of an object's position or configuration. Think of it as energy that's not going anywhere but ready to be unleashed. You might not realize it, but you've experienced potential energy many times, like when you stretch a rubber band or pull back a bowstring, you're storing energy. And when you let go, that energy jumps into action, turning into kinetic energy, energy of motion. Now, let's dive into one of the most famous types of potential energy, gravitational potential energy. Imagine you're holding a stone at the edge of a cliff. The higher up you are, the more potential energy that stone has because gravity is pulling on it. The higher the height, the more energy it stores, just waiting to fall. We can calculate gravitational potential energy using a simple formula. Potential energy equals mass times gravitational acceleration times height, or in symbols, V of h equals m times g times h. Here, m is the mass of the object, g is gravity, and h is the height above the ground. So, what happens when you drop the stone? All that stored potential energy gets converted into kinetic energy as the stone falls faster and faster. And trust me, that stone is more than happy to release that energy as it speeds toward the ground. Now, let's talk about how force ties into potential energy. Think about pushing something uphill. As you push, you're doing work to store energy in the object. The force you apply depends on how much potential energy you're storing in that object. Here's the cool part. The relationship between force and potential energy is given by a formula. Force of x equals negative dv of x over dx. F of x equals negative dv of x over dx. This tells us that the force is related to the rate of change of potential energy with respect to position. So, the harder you push, the more energy gets stored. For example, with gravity, the force acting on an object is simply F equals negative m times g. That's the force pulling everything toward Earth. And that's the force that's storing all that potential energy when you lift something up. Alright, let's take things up a notch. What happens when you release that stone from the top of the cliff? All that stored potential energy gets converted into kinetic energy, the energy of motion. And the faster the stone falls, the more kinetic energy it gains. The relationship between potential energy and kinetic energy can be described by the formula velocity squared equals to times gravitational acceleration times height, v squared equals to times g times h. This shows how the speed increases as the stone falls. The higher the stone, the faster it will be moving when it hits the ground. All that potential energy is now in motion as kinetic energy. It's just like a roller coaster. As it climbs, it's storing potential energy, but once it drops, that energy transforms into kinetic energy, and whoosh, the coaster races downhill. But what if forces like friction or air resistance are involved? These are called non-conservative forces, and they don't quite play by the same rules. Unlike gravitational force, which conserves mechanical energy, non-conservative forces like friction turn some of the energy into heat. Imagine sliding a box across a rough floor. As the box moves, friction works against the motion, and instead of just turning all the energy into movement, some of it gets turned into heat. The work energy theorem tells us that the change in kinetic energy is equal to the work done by the net force on the object. So, non-conservative forces waste some of the energy in other forms like heat. It's like trying to run while wearing sandpaper shoes. You're working hard, but some of your energy is lost. Let's shift gears to spring energy or elastic potential energy. Have you ever stretched a spring or a rubber band? Both store energy because of their deformation. When you stretch or compress them, you're storing elastic potential energy, and that energy is released when the spring or rubber band returns to its normal state. Hooke's law tells us that the force exerted by an ideal spring is proportional to the displacement from equilibrium. Force equals negative spring constant times displacement, F equals negative k times x. Here, k is the spring constant and x is the displacement from equilibrium. And when you release the spring, that stored elastic potential energy is released as kinetic energy. It's like a coiled spring, just waiting to unleash all its energy and jump into action. Here's where things get really important: conservation of mechanical energy. In a system with only conservative forces, like gravity or spring force, the total mechanical energy, the sum of kinetic energy and potential energy, remains constant. This means that as an object moves, it's constantly trading potential energy for kinetic energy and vice versa, but the total energy stays the same. For example, when a ball is thrown up, it's slowing down and losing kinetic energy, but gaining potential energy as it rises. When it falls, the reverse happens. The formula is simple: k of I plus v of I equals k of f plus v of f, k sub I plus v sub I equals k sub f plus v sub f, where k is kinetic energy and v is potential energy. The total energy at the start is the same as the total energy at the end, as long as no external non-conservative forces like friction are involved. To wrap it up, let's go over what we've learned about potential energy. It's the energy stored in an object due to its position or configuration, like a stretched bowstring or a ball at the top of a hill. When the object moves, the potential energy is converted into kinetic energy. This is a key concept in physics that helps explain everything from falling apples to roller coasters. Remember, potential energy is not just about what's stored, but also about how it can be released to do work, as we saw with gravitational energy and springs. And in systems with only conservative forces, mechanical energy is conserved. It just keeps moving back and forth between potential and kinetic forms. So, the next time you see a roller coaster climbing up a hill or watch an object fall, you'll know the potential energy at play and how it's going to transform into something else. See you next time with another exciting concept in physics.